All right, it's ready. 8. We'll start on time. Okay? I have to do a lecture and record it today in the morning because it's so important for both track 1 and track 2 as well. Just some general reminders. just still asking questions about the logistics over here and just make sure everybody understand it, right? I talked about this yesterday as well. Really quick before we dive into the physics of the MPU sensor, okay? Is that clear for all the tasks for both tracks? Any other questions? Is lab14 a regular lab? Yes. Can you drop it? Yes. If you choose to drop it, okay, but you have to work on the project today towards the end in order to get the TA to give you full credit. Okay? You can also choose to drop another lab from 1 to 10, depending on your choice. All right? So lab 14 is not a project lab. It's a regular lab. Keep in mind, it's a regular lab we are doing today. Let's take a look really quick. Very quick. Demos, blah, 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 7 demos really quick. Okay? Go to the in lab. Only 2 questions. Very doable. Get it done in 1 hour or less. Should be less. I mean, probably plus the soldering, I can expect, hopefully, if you can get it done quickly, 1 to 2 hours. Just get it done. So you have 1 hour left. To do what? To do this. What is this for track 1? Track 2, work on your projects. Okay? Track 2 projects. For track 1, do what? Come to course project task 4. Yes. In lab 15 and lab 15 demos, what are they? Take a look. What is in lab 15? 2 questions for in lab. And 3, 4, 5, 6, 7, what are they? Demos. Okay? What are the demos? Very fundamental. You don't need to develop new things based on what you just started today and just use that board, just do more demos. That's the only difference. Are there any overlaps? Yes. I forgot. I mean, I did the lab 14 in labs probably 1 week before, but there are only two demos are repeating, which is okay. I mean, just getting you double dipped and getting more credits. I already posted, don't want to change it anymore. But most of the demos are different. It could be a good thing, so it can remind you about all the procedure to go through all the setups. I've used the MPU sensor for many years, I can let you know. I built a balancing robot car and all this kind of stuff. So the most important thing, even though you are not programming the sensor, accessing the register yourself, however, there's one thing Dr. Carlson already programmed into the chip. What is it? O, okay? Case O is doing reset and enable. Keep in mind, you should always do that. If you see some data which is not making sense, make sure you have reset it. Very important. If you don't reset MPU sensor, it won't start operating, which is command case O here. So what that does is sending us, I think it's 00 something, I forgot. It's a 1 byte to that register to reset it. Very, very important. Then what you do, follow all these settings in the different cases and give a different number. So it's able to choose that kind of configuration to operate it in a certain condition. I'm going to explain what the conditions are really quick. That's why I'm here today in the morning. Very important. I'm recording this for other sections as well. Okay? Very important. What you are looking at is basically the Z-axis for lab 15 only. Okay? For your track 1 project, you probably need to get access to the acceleration and gyroscope readings and calculate the angles. But for the in-lab lab 15, it's basically just a demo. Look at the Z-axis. Get a reading of something around. Remember, I'm recording this. Come back to this video if you forget it, okay? Record something around 8,000 to 9,000. Should be somewhere around like 8,600 something. Because that's what? That's 1G. Let me show you really quick. What does that mean here? Okay, so the sensor is being configured at a range of plus minus 4g, which means it's able to detect two directions of acceleration in the terms of unit of g's. Okay, gravity in terms of g's, not grams. Gravities, okay? And that 1g represents what? 8,192 what? LSBs. So it's a digital analog converter inside. It's converting all the analog data into what? Into LSBs, which is basically just battery numbers. A battery number 1 will be 1 LSB. Does that make sense? Based on the reading, the sensor is giving you the reading. The reading is a very large number, and that number is basically just how many battery 1s. One battery 1 is 1 LSB. Okay? And that 1 LSB represents one of the digits over here. And if you have 8,192 LSBs, it represents 1G of reading. It's a 1G acceleration reading. So if you are reading like somewhere around 16,000, how many G's of acceleration you are experiencing? About 2 G's. Okay? Does that make sense? If you are expecting the acceleration of your measurement could be go beyond like 10 G's, which configuration you want to use? 10 G's. If you mount your sensor to a rocket, okay, you know that the launching process probably is going to experience like somewhere around, I don't know, 10G, 5G, I don't know. I mean, for example, 10G. Okay, you want to use acceleration entry number 4, which is 3 over here. Okay, this is a register, like the register have you used in PIC. It's a register, even though you are seeing a decimal number, but actually it's a 3-bit. How many bits I forgot? 3 or 4. Doesn't matter. It's a register that I can set up which configuration I want to use, depending on the range. I mean, for example, hey, I'm just experiencing plus minus 2G as a maximum, for example, okay? But can I still use a plus minus 16G range? Should I do that? It's overkill. What's the downside of it? It's reducing the resolution. You only have 16 bits of resolution. You're wasting so much in the range, in the dynamic range. Okay? Choose what you need. Don't do overkill here. Make sense? So if you read from the sensor, if you are reading 10,000 LSB, for example, that's a reading you have. Okay, that's whatever the reading. Look at the party reading here. Okay, party reading here. 8,000 something. This is a reading. Okay, this is a reading. If you have a reading, doesn't have to be 8,000, right? If a reading, for example, 10,000. Okay, you are using selection number 0 here. How do you calculate the acceleration? How to do it? 10,000 reading, right? LSBs. What is the acceleration? What is it? If I use the first entry here, how do you convert it? You need to know how many G's, right? So it's going to be 10,000 LSB divided by what? Divided by this number. So G will be flipped to the top, and you are getting how many G's? Make sense? Okay, that's how to calculate acceleration. What about gyroscope? Gyroscope measures what? Look at here. That's a sensor, okay? You can see a little dot. Pay attention to that little dot. Indicates polarity over here, a little dot. Okay? So acceleration, you can see X, Y, and Z, okay? X, Y, and Z, accelerations. For the people who arrive late, make sure you watch the video. It's super important, all right? Definitely watch it. So for the acceleration, it shows you the arrow for the positive acceleration, but it can be confusing. I'm going to show you why, okay? But now let's just assuming we know that this is positive acceleration X, positive acceleration Y by looking at the dot, so you'll know where's X, where's Y, where's Z, right? If I just place this sensor on the table on the desk, like this orientation, So Z is pointing up. Are you experiencing acceleration on the X and Y axis? Or are the chip, is the chip experiencing any acceleration on the X and Y axis? No, it's not moving, no force. X and Y is parallel to the Earth. It's no force. So that's why you should read zeros, almost zeros for X and Y. But for Z, you are complaining, hey, there's no acceleration on Z as well. It's not moving, right? But why the Z direction is reading a 1G data here? Yes, because of gravity, but how do we understand it? How do we understand what's really going on? So make sure that you know that if you place this chip like this on the desk, and Z is pointing up, X and Y is forming a plane in parallel with the Earth, X and Y are reading zeros and Z is reading a 1G. Okay, why is that? How do we understand it? What's really going on in the chip? It's really fascinating technology here. Why? Because accelerometer is the capacitive to digital converter. It's called CDC. Okay? What does that mean? It's measuring capacitance and convert capacitance to digital numbers. Okay? It has a very micro environment inside using silicon wires connecting little microsystems, and whenever it vibrates, the internal structure vibrates as well. It's a really fine structure inside, very fascinating. So what's really happening is you can imagine, for example, here's the box, okay? This is the Z direction, and this is a cross-sectional view of the chip. Okay, cross-sectional view of the chip. And you use a rubber band, connect the four corners of the box, very microstructure, okay, keep in mind. Microstructure in here. Rubber bands. Connecting a little box inside. Okay? Does X and whatever Y go inside moving this box to X or Y direction at all? There's no force towards the X and Y direction, but is there a force towards the Earth? Yes, gravity, right? So what's happening is this guy is gonna what? This little box will what? Like drop or, going up. Drop. This will drop, right? It's gonna drop. Because of the change of the location, since even though we don't know the microstructure, how that works, but by moving that little structure inside, it's gonna change the capacitance of the contact. It's not really contacting because it's making an electric field with other metal structures. So it's going to change the capacitance between this guy and whatever is making a capacitor with it. So it's changing the capacitance in the microenvironment. And that capacitance is being converted into a digital signal. That's how you are reading that LSB number over there. Whenever it drops, it has a location or position change. It's going to send out a capacitance change, and that capacitance change will be converted to a digital signal and then be converted into acceleration data. Okay? So that microstructure is being designed in the technology called MEMS. If you go to graduate school, probably there's a chance you will get into a MEMS structure in the clean room. It's called micro electrical mechanical systems. So the little silicon structures is connecting this guy. I mean, it's really interesting because if you make silicon or glass in a bigger structure like in touch, they are fragile. You can break them easily. But whenever you put them in the microstructure, the silicon wires and glass kind of silicon dioxide structures are super rigid. And it's very difficult to break them. That's why sometimes getting into the nano or micro scale, their features just got changed. Very interesting. So there's a little microstructure inside the chip, right? That tiny environment can vibrate and eventually change the capacitance rating and convert that capacitance rating to position changes and then to digital data output, okay? So in this case, even though it's not moving, however, based on the design of the chip, you can imagine it's equivalent to what? To moving this box where? In which direction? For example, if I don't have gravity, no gravity at all, I have a box holding. Inside the box, I'm holding a little box using the rubber bands Okay, so if this guy is dropping, okay, if I don't have gravity, if this guy is dropping, means this chip is moving to which direction? Up, right? So when it moves up, this one drops. So that's how the acceleration is being measured. That's why the z direction becomes what? Or whatever the status over here, if you have this chip sit on the table and this one drops, you should measure a what? If this is a positive reading of the acceleration, you should read a what? 1g or minus 1g. Even though it's not moving, but the box is dropping, right? It's very similar to the box is moving to where? And this is positive, right? So the acceleration along this axis is what? 1g or minus 1g? It's 1g, it's not minus 1g, keep in mind. That's why when you let the chip sit on the table, you are reading a 1g, even though the positive direction of that z is pointing up. Does that make sense? It's very similar. For example, x is pointing to that direction. If you look at the axis, x is pointing to that direction, right? So you know along that direction's acceleration will be what? For example, we are moving that one 1g in x. So if you move this box in that direction, it's actually giving you a 1g, right? And then the box is going to move to where? To the opposite direction. To the opposite direction if you move this box over here. So the box is going to be shifted to the left. So in that case, that movement of the box inside will create a capacitance change whenever this box is moving towards the left. So that's creating a 1g towards the right. Okay, that's why you are getting a 1g rating when you move it to the right. Does that make sense? Okay, let's do some calculations here. All right, so it's not moving this box at all, but it's using the gravity to let you understand what's really going on. For this one, see the dot is over there, okay? See the dot over here. It's like looking from here from the side, okay? So let me know, what is z? What is the z rating should be? We are using plus minus 2 g's, which is here, okay? Plus minus 2 g's. Plus minus 2g is the range, and this is the sensitivity, which is this many LSBs per g. So for this one, z is pointing up. So what is z's rating should be? 16,000 something, right? Okay? Does that make sense? Take a look. Z's, g's. It should be 1g, right? Z should be 1g here for case A. Okay? And the 16-bit 2's complement is what? For z-axis. For the first case. 2's complement for z. So just simply convert this one to what? To 2's complement, right? No, sorry, it's not 2's complement means here. So the I think it means 2's means binary number, okay? But the negative numbers will be 2's complement anyway. So z is in g's, in case A, it should be 1g, and 1g should be a decimal number of this guy, because this is this many LSBs per g. And convert that one to binaries, to 2's, and that is what? 163A4. Did you see the hex number here? Oh, I think it shows 2's, but you can combine the 4 digits into hex numbers and just show a hex number instead of 2's. Okay, for the table. So what you want to put in that table, in that location there, like I showed you here. What you want to put in here?
4000.
Yeah, 4000, 4 and 3 zeros, like this guy. Okay? Make sense for this case? Now let's look at a tilted version. See if that makes sense. Okay, let's take a look at this one. So you can see that this axis is not changing, it's just rotating, but it's not changing the direction towards the gravity because that's the only acceleration you have. Okay? And z does change, but it's not asking for z here right now. Let's consider x. This axis, the arrow I draw here is x. Y, let's go back to the, let me make a snapshot, it's easier to compare. Okay, take a look. See the dot is over here. The dot is over here. Dot is over here. Do you agree with that? This axis is x. See here, x. Right? It is x. And remember we give you the example over here when I let the sensor sit on the desk, z is pointing up and you are reading a 1g. Since we already understand it, let's just remember this right now, okay? So in that case, the direction opposite to the z's direction will give you a negative 1g. Let's remember that. The direction opposite to that arrow will give you a negative number here, okay? Now, let's come back. Let's look at x. X is pointing in that direction. That's the arrow's direction, sorry. That's the arrow's direction. So the component or effective gravity from the this gravity's arrow being applied to this direction will be 1g over square root of 2, which is cosine or sine, whatever, 45 degrees. Okay? And add a negative sign in front of it. Does that make sense? Because it's along that arrow, so that's why I have to add a negative sign in front of it, since we already understand what's going on. Whenever it's going opposite to the z direction, it's giving you a positive number, but whenever it's along it, it's giving you a negative number. Let's just remember it, since I already went through that. You understand that? So now, whenever this one is having an effect along the direction of the arrow, it's giving you a negative number, which is negative g over square root 2. So, let's see. For case C, and now let's look at case C's x. See if that makes sense. Case C, x, is giving you a negative number. Okay, we already verified it. Remember, if it's along that arrow of that direction of the axis, you are getting a negative number, okay? So that's why we're adding a negative number in front of it. So how to convert it to a better number? Could you stop talking a little bit? I'm sorry? Hey. So what about the better number here? If you convert this one to a binary. So where to get started? What is 1g, remember? What is 1g? This is 1g, right? This is 1g. So 1g divided by square root of 2 is what? 1g divided by square root of 2 is giving you 11585. That's the effective acceleration from the gravity applied to this x-axis. So that is 11585. Okay? 11585. However, it's negative. So what you want to do? Go back to the programmer and use what? 0 minus 11585 to get a negative 11585. Okay? So negative 11585 will show you a 2's complement number here, which is D2BF. So D2BF should be put in here. That's the reading you are going to receive. D2BF. Okay? Sometimes you'll see a positive 45 degrees. So that becomes what? Positive 11585 is giving you what? 2D41. Okay? So for this case, for case G over here, is what? 2D41. That already covers the both the positive and negative 45 degrees. So what about 1G positive? 1G positive. What is 1G? This is 1G, okay? So 1G positive is 4 triple zeros. Okay? So what is 1G negative? That happens, right? You flip it. It's going to be 1G negative. What is that? 0 minus. What is it? C triple zero. Covers all the cases. You just have to use your own judgment, like which one applies to which, okay? Try to record it. You should be able to do it. Do you have other cases? It doesn't even show other cases, like 30 degrees. No. It's either 0 or 1 or 45. Makes sense. Okay? You should be able to fill up all the cells over here. So what about gyroscope? What does that mean, gyroscope? It's a rotation or angular velocity. It's not just a linear or one-directional movement. It's rotating. So if you look at this one, let's take X for example. If you rotate the chip along the X-axis, and it's going to read a data through the gyroscope and showing you how many degrees per second. That's what we want to know. How many degrees per second? Let's take a look at the table. Take a look at the table. You can have 4 different options, okay, with different ranges. If you expect your machine is going to rotate faster than 2,000 degrees per second, use number 4 or case 3. If you expect your machine will not spin faster than 250 degrees per second, use the first one. Okay? And these are the corresponding LSB ratings per. Use the unit here as one entity. Okay? Don't split them. So this many LSBs per angular velocity. So this many LSBs per degrees per second. Let's take a look at the example. It's very similar stuff, okay? So now, my gyroscope read a D368 data in here. This is my reading. That's what I can see in the body, right? So I'm asking you to calculate the angular velocity, my airplane, how fast my airplane is rotating, so I can adjust it without having a crash. Okay? Angular velocity. What's the range I'm picking up? 500 degrees per second. And where is it? Oh, the second one. 500 degrees per second is using 65.5 LSBs per that angular velocity. All right? So whatever LSBs I'm rating, I want to divide that number by this number, or I want to multiply that number by this number. Answer me now. Let me know. I'm getting, for example, 1,000 rating. 1,000 rating. But I want to get the angular velocity. So what should I do? I want to use, let me see, let me show you. Okay. Divided by 65.5 LSB per degree per second. Okay, so after the divisions, it cancels, it flips to the top, so you're getting degrees per second, which is the angular velocity. So for the rating, you divide that rating by this number. Okay, that's what you do, what you want to do. Come back, take a look. First one, so you have 2 directions to rotate. So if I'm getting a D, So D, you know the MSB becomes a 1, so 2's complement is a negative number, right? So that's why you want to do this. In here, use 2's complement, have choose word. I didn't choose it, but now let's choose word, okay? Let's type, choose hex, and type D368 here. So you are reading negative 11414. That's the binary reading you are going to see from the gyroscope. That's the reading. How to convert it? How to convert it to angular velocity divided by 65.5 lsbs per degree per second. Okay? Do that. Let's see. (11414) divided by what? 65.5. Boom. Negative 174 degrees. Negative 174 degrees per second. Make sense? How long it takes to get this change? 0.1 seconds. And we're not programming it, but in the future you should know how to do it. But now let's just use, because it's degree per second, and this is how long it takes to change that much. So use this time times the angular velocity, you're getting how much degrees has changed. So this times this to get this. Make sense? I don't want to spend more time today since I need to give you time to do the soldering. Okay, so the parts are over there. Pick up the parts. How that works? Pick up the board first. Pick up the board first. And what you want to do is go to the lab in EDC. Okay, do you know what flux is? Flux for soldering. So flux is a material, it's acidic material, can remove the oxide layer of the metal. Because the PCB, whenever it's getting fabricated, it's exposed to the metal, to the air. The oxygen will oxidize it. So the metal will have a very thin oxide on the top, but you couldn't see. But the thing is, that one will prevent the solder from sticking to the metal. So the problem is you want to use flux, which is yellowish kind of gel in the syringe, in the fridge. Apply that one to the pads first, every single pad, every single one. So whenever you heat it up, it's able to remove the oxide on the metal and let the solder to stick to the metal. So it's helping your soldering like 100 times. And apply flux first to make it sticky, so you can pick the parts and place the little parts onto the pads so you can hold it, right? Have the parts ready and transfer it to the EDC and to the soldering. You can either use a soldering iron on the tip to solder it. I can show you how to do that. Or you can use a hot plate. But we only have one hot plate, so it's going to be crowded. So if you see people are already using that hot plate, try to use soldering irons. We have so many soldering irons in the lab. It's doable. These 1206 chips are huge. So you can do that. If you don't know how to do that, I will show you how to do it. Solder it. Don't spend too much time. Finish it. Do the demo to the TA. Try to finish both. If you're track 1, try to finish both lab 14 and 15 at the same time today. And if you're in track 2, only do lab 14. Lab 15 is optional. Does that make sense? Okay, let's start working on it. So the cart over there, the parts are in the cart. The boards, the parts, and we don't have one of the components we don't have, which is 10 microfarads, I think. But if the capacitor, let me show you really quick. If the capacitor is doing this, like VCC and GND, okay, 10 microfarads. Oh no, sorry, it's 4.7 microfarads, I believe. It's just a low pass filter. It's just trying to couple the AC noise to ground. It's not doing anything else. It's not a functional component. You know what I mean? AC pass, AC noise. So this is AC ground. So what's happening is the AC noise affecting the stability, the stability of the DC power source will be coupled to the ground. It's just removing the AC noise. So it doesn't matter. If you don't have 4.7 microfarads, just pick like 10 microfarads. Something similar. It's going to work. Don't worry about that, okay? Okay, let's get started.